is a problem in which we compare two scenarios with and without friction. And in the scenarios, in this setup, what we have is two masses, identical masses that are connected by a rope and being pulled to the right by 100 newtons, and they're accelerating in this direction, so there's no equilibrium. This is the situation in which Newton's second law is going to apply. And the question is, in these setups, where the difference is here, I have no friction surface and this surface has some kinetic friction. In these setups, what is the tension in the rope connecting the two masses in these two cases, friction and no friction? So let's start with the frictionless case. And in that case, I can solve this in a number of ways, but I'm going to take the slow way. I'm basically going to isolate each of the masses, and I'm going to look at the free body diagram for each of the masses, and I'm going to see if I can figure out an equation for the tension in here. So if I isolate this mass on the left and I look at the free body diagram for this mass on the left, I know that it has some weight, the attraction of Earth to the mass, and I know that the surface is going to respond with a normal force. And I know that in the x direction, because there's no friction, the only forces that is going to be is the tension in the rope that is pulling that mass. If I look at the free body diagram for the mass on the right, I know that it's also going to have gravitational force towards the center of the Earth. The surface is going to respond with the normal force. This is Newton's third law. And of course, there's the force that is pulling it at 100 newtons. And there's the tension in the rope that is pulling the other mass, right? The mass is pulling on the rope with tension T, so the rope is pulling on the mass. And when I'm drawing the free body diagrams, I'm looking at all the forces exerted on the mass or on the object, not by the object. So the object is pulling the rope, so the force on the rope would be in this direction. However, the rope is pulling the mass, so the force on the mass will be in the opposite direction. Same thing here. The rope is pulling on the mass in this direction, and the mass is pulling on the rope in the other direction. So I'm looking on the forces exerted on the masses. So, okay, let's solve this. Of course, in this case, the normal force is going to be equal to W because there's no movement in Y, no acceleration in Y, but that's not really going to help me. What's going to help me is if I write the X equation, and in the X equation in this case is the net force in X, which is just T, is going to be equal to the mass times the acceleration in X. So the net force, which is T, on this direction is the acceleration multiplied by the mass that's being accelerated. Okay, and from this free body diagram for this mass on the right, again, the normal force in this case is also going to be equal to the weight, but it's not going to help me much. What is going to help me is if I write in the x direction. In the x direction, I know that 100 newtons in the positive x is, if I subtract from it t, because t is in the opposite direction, so if I'm adding vectorially the 100 newtons and the t, this is the net force in x, and that's also going to be equal to this mass, the mass that I'm examining, multiplied by the acceleration, because the system is accelerating with the same acceleration. And now if I combine these two equations, let's say I'm going to call this equation 1, I'm going to call this equation 2. I'm going to combine these equations in the following way. I'm going to subtract equation 1 from equation 2. So the way I subtract these two equations is I'm going to take the left-hand side, I'm going to subtract 2 minus 1, and in the right-hand side, I'm going to subtract 2 minus 1. So for the left-hand side of the equations, 100 Newton minus T minus equation 1, so minus T. And on the right-hand side, it's going to be MA, and then minus the right-hand side of the other equation. So from this, I find out that 100 newtons minus 2t is equal to 0, which tells me that t is 50 newtons. Now, if I want to solve part B with the friction, then I'm also going to draw the free body diagrams. So for the mass on the left, it has some weight. The surface responds with the normal force, but and I know this normal force is going to be equal to the weight because it's in equilibrium in y. However, the surface is also going to respond with a friction force. In this case, because mu k is not 0, the coefficient of kinetic friction is non-zero in this case, and the friction force is going to be equal to this coefficient multiplied by the normal force, which in this case is equal to W. So I'm just going to write it this way. And of course, there's the tension in the rope. For the mass on the right, I know that it has some weight. I know that it has the surface responds with some normal force that is equal to that weight. Notice that I labeled it the same weight because it's the same mass. So in fact, I can write it just as mg because it's the same mass. And now the surface has some friction, and that friction is going to be proportional to the normal force. So it's mu k times the normal force, which in this case is W, which is also mg. And it's being pulled by the 100 newtons. And of course, let's not forget the tension in the rope. Okay, so let me write the equations again. So from the y, we figured out that the normal force is equal to W, the weight, which is equal to mg. And that tells us that in the x direction, if I'm choosing this to be my x hat, my positive x hat the whole time, then I'm going to write t minus mu k times W, and W is equal to mg, so I'm just going to write it this way. And this is going to be equal to the mass, this object that I'm isolating, times its acceleration. So this is Newton's second law applied to this object. If I apply Newton's second law to the object on the right, I've already done the equilibrium part in y, which says that these two forces are going to balance out. So from that, I know that the normal force is going to be equal to mg. And from that, I know that the friction, because it's proportional to the normal force, is going to be mu k mg. And plus t is going to oppose the 100 newtons. And of course, there's acceleration. So if I write that, so I'm going to call this equation 1 again. I guess I could call it 1 star because just to differentiate it from the equation 1 on this side. And equation 2 star is going to be, I'm going to take 100 newtons in the x hat direction and subtract from that t, and subtract from that as well mu k mg. And these are going to be equal to this mass, which also happens to be m, multiplied by the acceleration of this object would also happen to be a. And I'm going to call this equation 2 star. Now, what I want to do next is I want to find t. And if I add the two equations, t is going to cancel out because here's a t and here's a minus t. So if I want t, then I would like to subtract the two equations. So if I look at 2 star minus 1 star, I will get 2 star. First of all, I look at the left-hand side. I just write 2 star as is. So 100 newtons minus t minus mu k mg. And then I subtract from that the left-hand side of 1 star, so minus t. And then minus minus, that's a plus, mu k mg. And on the right-hand side, 2 star is ma. And then I'm subtracting from that 1 star, which is also ma. So this is going to be 0. So I see here that I get the 100 newtons I get a minus t and a minus t, so that's minus 2t. I get a minus mu kmg plus mu kmg, so these cancel out, so that's a 0, is equal to a 0. And from that, I figure that T is equal to 50 newtons. So in fact, in this case, it so happens that the tension in the rope is equal to half the force I'm pulling with, because both masses are suffering the same amount of friction because they're identical masses. And whether it's that friction is 0 or that friction has some value, both of these values are equal. That's why to move with the same acceleration, both masses, I could take the full force divided by both masses, and that will tell me how much each mass is accelerating, and that tells me that this tension has to be equal to half 100 newtons.